Hello, my name is Lexi Goldman, and in this video, I will be presenting my absorption spectroscopy mastery assignment. The first concept is accurately describe the relationship between the absorption and transmission of light. Absorption is the amount of light that is absorbed by a solution. Transmittance is the amount of light that passes through a solution. Absorption and transmission of light have a logarithmic relationship and are complementary to one another. This means that as more light is absorbed by a solution, less light is transmitted. The opposite is also true. As less light is absorbed by a solution, more light is transmitted through the solution. We can see this relationship in the graphs. As concentration increases, transmittance decreases exponentially, whereas absorbance increases at a roughly constant rate. These graphs show the logarithmic and complementary relationship between absorption and transmission of light. The second concept is accurately describe how transmittance is determined from light intensities. Transmittance is defined as the intensity of light after going through a sample divided by the initial intensity of light before going through the sample. The equation for transmittance is on the slide. Transmittance can also be expressed as a percentage by taking the equation for transmittance and multiplying it by 100 in order to get a percentage. The diagram shows how the initial intensity of light is the light before it hits the cuvette, and the intensity of light after sample is the light that passes through the cuvette and is present on the other side. The third concept is accurately describe how absorbance is determined from transmittance. The equation for absorbance is negative log of t, where t is the decimal form of transmittance. We can see from the graph that absorbance and concentration have a linear relationship and a positive slope. Therefore, the data is much more simple and straightforward to look at. Because of this, it is much easier to determine absorption using absorbance rather than transmittance. The fourth concept is accurately describe Beer's law and what sample parameters affect the absorption of light. The equation for Beer's law is listed on the slide. Beer's law states that absorbance of light in a sample is directly related to the molar absorptivity, path length, and concentration in molarity. The epsilon in the equation represents molar absorptivity, which is a constant value dependent on the wavelength and is an intrinsic property of the molecules being observed in the sample. Molar absorptivity can be listed as inverse centimeter inverse molar and written as 1 over centimeter molar. The b in the equation represents path length, which is the distance the light has to travel through the solution. The path length is the cuvette width. The c in the equation represents concentration, which is expressed as the molarity of the solution. Sample parameters that affect the absorption of light include path length and concentration. For example, if the path length, aka the width of the cuvette, is longer, then the absorbance will be higher because the light has to go through more solution. If the path length is shorter, the light has to travel through less solution and the absorbance will be lower. If the solution is more concentrated, the light will interact with more molecules and therefore the absorbance will be higher, whereas if a solution is less concentrated, the light will interact with less molecules and the absorbance will be lower. The final concept is accurately describe a typical setup for an absorption spectroscopy measurement. The three components of the transmission of light are the light source, the sample, and the detector. We can see from the diagram that the light source is on the left passing through the solution, the sample is in the middle, in the cuvette, and the detector is all the way on the right measuring transmittance. The light source is what passes through the solution in order to measure absorbance. The light that is transmitted are of all the colors and wavelengths besides the complementary color of the solution. The light that is absorbed is the complementary color of the solution and its respective wavelength. We can see from the color wheel on the slide that the complementary color of a solution is the color opposite of the color of the solution. For example, the complementary color of green is red. Therefore, we can see from the graph that the most absorbed color of green dye is red. This is important later when I choose the wavelength setting on the colorimeter because the wavelength used is whichever measures the highest absorbance of the solution, as that is the wavelength of the complementary color. I will expand on that more in my practical video. The sample is in the cuvette, and this is what the light passes through in order to find transmittance and absorbance. Lastly, the detector determines how much light is transmitted through the solution by measuring how much light is present after passing through the solution. To begin, I cleaned off the cuvette filled with the stock solution and held the cuvette on both sides with ridges so I didn't get any fingerprints on the cuvette that would interfere with the measurement. I placed the cuvette in so that the arrow, which signifies where the light passes through, was pointing at the smooth side. This ensures that the right path length is used and that no ridges interfere with the transmission of light. Next, I scanned through the wavelengths to find the one with the highest absorbance, which will be the wavelength of the complementary color. Since my solution is blue, the complementary color is orange. Therefore, the wavelength with the highest measured absorbance is the wavelength of orange, 635 nanometers. Next, I cleaned off the blank, which is deionized water, to ensure fingerprints wouldn't interfere with the measurement, and calibrated the colorimeter in order to set it to 0 before measuring the absorbance of the solution. Since the deionized water is transparent, all light will pass through and the absorbance will be set to 0. This is important so that the absorbance is only a measure of light absorbed by the solute, the blue dye, rather than the solvent, the water. I clicked the cal button, and when the red LED stopped flashing, it was calibrated. Then I cleaned off the sample, held it by the ridges, and placed it in so the arrow was pointing at the smooth side. I closed the door in order to determine the absorbance, which is 0.206. That completes my absorption spectroscopy mastery assignment. Thank you.